In this video, I'm going to look at the ESP32 microcontroller. This is a popular microcontroller for hobby electronics, providing a way to interface with electronics wirelessly. In this, I'll show how the ESP32 can be used to provide a network interface to electronic components. I'll then explain how you can control the devices of a Raspberry Pi or even a mobile phone. Finally, it will show you how you can use a graphical interface on a Raspberry Pi able to control a remote ESP32. So first we'll cover what the ESP32 is, how to set up the Arduino IDE for the ESP32, start with a simple Blink program, give a practical example, and I'll be using Model Railway Lighting, how to create a web interface, and how to use Pygame Zero graphical user interface with the ESP32. So the ESP32 is a microcontroller that's similar to the Arduino and Pico that I've looked at already. The ESP32 has advantages in terms of speed. It's certainly much faster than the classic Arduino, and its clock speed is higher than the Pico, although performance really depends on what you're using it for. The ESP32 microcontroller is the silver coloured block at the right hand side of this image, and it includes this antenna at the right hand side. This complete circuit is actually a development board which is designed to provide access to the GPIO pins. I'll cover this in more details later in the video. So the main reason to consider the ESP32 is its built-in wireless capability. It includes an ability to use as an Internet of Things device without needing to be tethered to another device. There is a downside, and that is it's a little more expensive than the Pico, although it's still less than an official Arduino. For hobby enthusiasts, the difference in a few pounds shouldn't cause any problems, but it's something you may want to consider if you need a lot of them. Another downside is that it's not quite so well supported or documented as some of the other microcontrollers. Both the Arduino and Raspberry Pi have a huge community behind them, and whilst the ESP32 is popular, you may find yourself having to interpret documents and search for references compared to the step-by-step guides that are provided for the Pico, for instance. To be clear, there is lots of documentation about the ESP32, especially as its popularity has increased. It's just not so easy to find the documentation or get community support if you need it. So the ESP32 is actually a series of microcontroller chips produced by Expressive Systems in China. The ESP32 is the second generation of devices which replaces the ESP8266. The particular board I'm using is an AZ ESP32 Dev Kit C V2 ESP32-WROOM-32. Quite a mouthful. There are newer versions of this board available, but most work in a similar way. You should be aware of the different pin out that some boards have. In the case of this particular board, you can look at the labels on the PCB itself. As I've said, there's wireless capability, and that's provided through Wi-Fi and Bluetooth. In addition to that, there's also analog to digital converters, digital to analog converters, capacitive touch switch sensors. It supports SPI, I2C, or officially known as I2C, I2S, UARTs. It includes a Hall effect sensor, and it's got other specialist interfaces. Which of these particular features are available and how many depends on the board and the way that you plan to use them. For example, some of the features share physical pins. So if you're using the pins for something else, then it may prevent you from using some of the features. It's possible to program the ESP32 using the toolchain provided by Expressive, but the alternative and perhaps easier way is to use the Arduino IDE. And the Arduino IDE is a platform that many will be familiar with, and it's easy to configure, so it's the one I'll be using here. And I'll be installing it on a Raspberry Pi and using the Raspberry Pi to configure the ESP32. So here I'm going to show you how to set up the Arduino IDE environment on a Raspberry Pi using Raspberry Pi OS. The code that runs on the Raspberry Pi uses some Python code running from the IDE, and this needs to be on Python 3. So whilst Python 2 is now considered depreciated, some Linux distributions, including the current version of the Raspberry Pi OS, still default to Python 2, which means it won't break if there's any legacy code. In most cases, it should not be a problem to switch, but there is a chance it could cause some problems. So the method I'm going to use here is specifically for Debian-based distributions, including the Raspberry Pi OS and Ubuntu, and this will make it easy to switch back if you need to. So the command to do this is sudo update alternatives -- install, then usr/bin/python, which is where the link will be created, Python, which is what it's to do, and then the path to the Python interpreter, and 2.7, and then number 2. Now we do the same for Python 3 using Python 3. Then sudo update alternatives -config Python, and this will allow us to choose which particular one. It's now gone to Python 3. We'll just do that just to make sure, and we can test what version we're at now. So that's the Python setup. And if you need to go back to Python 2, you can just use that same command -config Python and choose 2. Now that Python's been set to version 3, download the latest version of the Arduino IDE from the arduino.cc website. There are versions of the IDE in the repositories for various Linux distributions, but they are very much out of date, the ones I've had, and so may not work very well. So I suggest you get the latest version. In the case of the Raspberry Pi, using Raspberry Pi OS, then you want the Linux ARM 32-bit version, which I've already downloaded. I'm going to install that into the opt folder. So here's the file here. I changed it to /opt. I'll have to run this as root using sudo. Now that's installed, you could add it to the start menu, but for me I'm just quite happy to run from the opt directory. So after installing the IDE, you need to add the board to the board manager, and before we can do that, we have to go into the preferences and add it as an additional board. This additional board URL will explain how to install the board. So I've copied and pasted this. It's quite a long URL. It's linked on my website, so you can just get the details from there, and then you click OK. Now we should be able to go into board and the boards manager, and we search for ESP32. It brings up ESP32 by Expressive, and that's what we need, and we'll just install the latest version. Now that that board's been installed, I can connect the ESP32 board and we can choose the appropriate board. So I'm going to use ESP32 Dev module, and if I use a new tab, so if I look at the D message, which shows the ring buffer, I can see that this is the device that's been added, and here we go. So it's on TTY USB 0. And in the Arduino, we can now choose the appropriate port, USB 0. In the Arduino IDE, there is a blink example. You can see that in the examples, basics and blink. We would just need to make some slight changes to that. Here's another version. Again, the source code's available on my website. I've copied and pasted it, so it's added some extra spaces, but we can just ignore those. And then if we upload that, we just need to give it a name. So it's going to compile. So that's compiled and uploaded the code, and it's set the onboard LED blinking on the ESP32. So for a practical example, I'm going to show how this can be used as an alternative to the Raspberry Pi hat, which I've created for my Christmas house project. In that project, I created a model house with colour changing snowman and decorative Christmas lights. This is based around the same 3D printed building, but it's slightly more basic functionality. I'm not going to have the Christmas lights on. Instead, this has just got an internal light, a flickering fireplace made up of 2 LEDs, and an optional smoke generator for the chimney. This is a version based around a Raspberry Pi or other device, and then using the ESP32 controller within the house. I'll be using C for programming the ESP32, as in the blink example, although I will be using Python for the graphical user interface, which I'll cover later. I'm just going to show some of the code that is required for this. So the network feature of the ESP32 allows you to configure the ESP32 as a web server. This can be used to provide a client server setup where the ESP32 acts as a server, the user interface on a remote computer such as a Raspberry Pi or even a mobile phone, and then this can be used to create a GUI application, which I'll be using on the Raspberry Pi. This can be provided over a local network or over the internet through IoT, Internet of Things. In this project, I've connected both the ESP32 and the Raspberry Pi to the same local network. The library I'll be using is Wifi.h. This is the initial code, includes Wifi.h. So this is the library that supports the use of the Wi-Fi on the ESP32. I've entered the SSID and the password for my local network. Obviously you just change those to whatever your network uses. IP address gateway, this is because I'm using a static IP address so that I can access it using its IP address, and uses a Wi-Fi server running on port 80, which is the default HTTP port, and then it's got some initialization code. Then the rest of the code goes in the Arduino loop. and this basically listens for incoming clients, and then when they're connected, checks that they've got data for them to send and stores this into a header string. So this is the get information that you'll use to determine what it's asking you to do. And then it's going to send, when it reaches the end, which we know because there's no longer any incoming data, then it's going to send its response. And that's handled here. At the moment, it always sends a code 200, which means OK, and this part of the code is where you would add your own, return your own HTML to give you your user interface, and also to handle the incoming instructions. And all this is available on the code that's linked in the description. And then when a client disconnects, then it just runs the client stop. So once you've got this running, compiled and uploaded, it will run continuously and be able to connect from a web browser. But first we need to add some electronics, basically connect the LEDs that we're going to use. So here's a schematic diagram. It's very basic, quite straightforward. So basically we've got three LEDs here, a white LED, and these are red and yellow to represent the flicker of the fire. And then the only one that's a bit more involved is the smoke generator. This generally runs at much higher voltage, at 12 volts to 20 volts. And so I've used a MOSFET as a switch to turn this on with a resistor, just to limit the current going out of the GPIO ports. I've already created a separate video explaining the MOSFET as a switch, so if you want to understand more about how that works, then you can see that as well. And then here it is on a breadboard. So the particular board I had came with the headers pre-soldered on, which allows you to plug it into a breadboard. There are a couple of potential issues there. One is that the pin space is not quite the same as the breadboard layout, so it wouldn't quite line up. Could have got it in if you pushed it, but found that I could space this better. Also, that if you pushed it in onto a breadboard using a single breadboard, one side would only have one row of connectors available, so it would be quite difficult to use. So what I've done is combine two breadboards here, and as you can see, there's each breadboard comes with a power strip as well. So these are the vertical, as you look at these, vertically connected, and these are horizontally connected, intended for power. But I wanted only one pair of these, so they can be removed. They've just got a sticky plastic on the back, which I just had to cut off to remove it off one of them, and then you can join two together, and it gives really nice spacing. It gives you two pins on each side, and then you've got three on the other side, so that works really well and gives you lots of space. So that's the way I like to do it, and as you can see, I've just wired it up as that schematic diagram. These LEDs with the resistors, current limiting resistors. The MOSFET is connected through a resistor, and the smoke. So I've just I haven't shown the separate power supply here, but you would need a separate power supply here that would go, say, your 12 or 20 volts to this rail and to this rail for the ground as well. And then with that all wired up, you can run the code and then connect using a web browser. And this is what it looks like as the interface. So this can be connected to from any web browser on the same network, and that could be a PC or a mobile phone. If you want to enable this over the internet, then you can do so, but you need to enable port forwarding on your home router and perhaps use something like dynamic DNS to give it a more user-friendly host now. Beware though that that would then allow anybody on the internet to be able to turn the LEDs on and off, because there's no authentication included in this. I'll be using mine on my own home network, so it's only accessible to those with my home Wi-Fi password, so that's a better solution. And I've not included the smoke generator on this web interface, but no, even though it's not on there, it will not stop anyone turning it on and off, as it uses the same URL as the other lights, just using the light numbers as 4. And you can see this is how it is coded. When you click on one of these, it uses switch on or switch off or flicker and then the light number. I'll just give you a quick demonstration of this. So here it is on my laptop computer. I've just gone to that web address, and as you can see, it starts with these in the off position, and we can turn them on or we can set them to flicker, and we can turn them off as well. So that's a very simple interface that allows you to control the LEDs. So the final step for this is that I wanted to be able to control the lights using a graphical interface on a Raspberry Pi, and believe it or not, this is actually the graphical interface to communicate with the ESP32. So I've taken my existing code and I've modified that so it still uses Pygame Zero, which is providing the interface, but now instead of controlling the LEDs directly as it did before, it uses URL lib to send an HTTP request to the ESP32. The code uses 3 actors which represent the window, and this one is used to turn the inside light on and off. A pile of coal here represents the fire, so it flickers the red and white and yellow LEDs. And the chimney is the third one, which creates this cloud of smoke, and that's tied into the smoke generator. So clicking on any of these will result in the URL lib request being sent to the appropriate light on, light off or flicker command. There's no error checking in this, although I have wrapped the URL request in a try except loop to prevent the GUI from crashing if the ESP32 server is not available. And clicking on the fire will cause both the red and yellow LEDs to flicker. This screenshot shows them all activated. So here you can see if I click on the light on the window, it turns the light off inside, and clicking on the fire causes the light to flicker, and the smoke generator will cause the smoke to come out. So this project has just been a simple demonstration of how you can use an ESP32 to allow LEDs to be controlled using a web interface. The ESP32 includes a powerful microcontroller, so it can be used for far more than this demonstration has shown. There is also a good chance that you've used the ESP32 or similar indirectly when using built-in Wi-Fi on other microcontroller boards. ESP32 is a popular choice for the Arduino Wi-Fi enabled boards and some of the boards based around the processor in the Raspberry Pi Pico. I've used the Arduino Wi-Fi boards in the past. I'll be covering other boards such as the Arduino Nano RP2040, which is the new Arduino based around the Raspberry Pi Pico processor, and that has a Nano W102 Wi-Fi controller which is based around the ESP32. And I'll be using those in the near future. If you've enjoyed this video, please give it a thumbs up and please consider subscribing if you haven't already. I look forward to seeing you again on my next video.